Uncertainty and the Social Planner's Problem, Why Sample Complexity Matters, by Cyrus Cousins. Machine learning systems are often trained on one group and then applied to other groups. From the Gender Shades project, we know that commercial machine learning systems for facial recognition are very good at recognizing light-skinned males, but perform poorly at recognizing dark-skinned or female people. This differential performance leads to algorithmic discrimination. We know that standard methodology learns unfair or discriminatory models. What has gone wrong here? Is the problem from what a machine is learning or how a machine is learning? The learning objective and the training data both play a role in model fairness. Unweighted risk minimization should be a conscious choice, not a default. Fair learning should optimize fair objectives. This is one, but by no means the only, reasonable choice of learning objective. Minority groups are also often underrepresented in training data. We ask how much data is required per group to train a fair model. Let's look at an example. Suppose a population with one disadvantaged group and G-1 privileged groups. Within each group I, utility is Gaussian distributed. The disadvantaged group has Gaussian 1-1 distribution, and privileged groups have utility distribution with mean at least 2 and variance no more than 1. We want to epsilon delta estimate the egalitarian welfare over these groups. In other words, we want some W hat that approximates the egalitarian welfare, or the minimum of the expected utility over each groups. By the Gaussian Chernoff bound, it is sufficient to draw m equals 2 log g over delta over epsilon squared samples per group. However, most of this effort is wasted on studying the privileged groups. An adaptive strategy would note that we only need 2 log g over delta samples to determine if a group is privileged. Once we do so, we can stop sampling from that group because they will never be the minimizer. This adaptive strategy has a sample complexity approximately a factor g better than the naive strategy. We know sampling is expensive and we want to allocate limited resources efficiently. So how do we take this idea that worked in this special case and use it to treat the general problem? This work addresses many such questions. Can the welfare, Malfare, and regret group-level fairness objectives be given a unified statistical and philosophical treatment? This would include the minimax fair learning, multi-group agnostic pack learning, and fair pack learning settings. Given MI samples for each group I, how sharply can we bound our objective? Statistical guarantees for estimation and optimization of fairness objectives are our goal. Finally, how should we efficiently allocate sampling effort to optimize an objective? Does the answer depend on the objective at hand? And can we efficiently allocate sampling effort without a priori knowledge? In this work, we generalize, unify, and analyze 3 disparate fairness concepts. Welfare summarizes overall well-being across multiple groups. This generalizes utility maximization to multiple groups. Malfare summarizes overall ill-being. In other words, we generalize risk minimization to multiple groups. And regret measures the amount lost by compromising on a shared solution. Fairness objectives mathematically encode the values of a society. There is no best or most fair objective. Different axiomatizations give rise to different objectives. Each objective is tautologically best for the fairness concept that it encodes. This work analyzes a broad swath of such objectives. We do not take a stance on which objective one should use. However, we do show that some objectives are easier to learn than others. In standard machine learning, we have some instance distribution D, and learning tasks are often cast as risk minimization with respect to some loss function L. In other words, we want to identify an approximation of H star, which is the minimizer of the expected value of the loss function. In fair machine learning, different groups have different needs and preferences. We thus consider distributions D1 through DG over groups 1 through G. A Malfare function summarizes overall harm across this population. We then cast fair learning tasks as Malfare minimization. In other words, we're looking for the H star that minimizes the Malfare operator applied to the expected loss of each group. Of course, we do not know the distributions, so we have to work from training samples, and we select some hat H that will optimize an empirical Malfare estimate. We should compare this to maximizing welfare, as both are instances of the social planner's problem, and both can be applied to various fair machine learning settings. Suppose we have some vector S1 through Sg representing utility or loss across multiple groups within a population. For the case of p not equal to 0, the power mean is defined as the pth root of the average of the pth power of utility or loss values. For the 0 case, we get the geometric mean, and for the plus minus infinity cases, we get the maximum or the minimum. We can think of the power mean as a smooth interpolation between the minimum, arithmetic mean, and maximum, and there are other special cases of interest. Power means are welfare functions for p less than or equal to 1, and also Malfare or regret functions for p greater than or equal to 1. So given some Malfare objective M and a hypothesis space H, we know that there exists some optimal H star in our hypothesis set. We want to select or learn some H hat in this set. In particular, H hat should be almost as good as H star. We want it to be epsilon delta probably approximately correct, by which we mean that with probability at least 1 minus delta over the training data, the Malfare of our learned H hat should be less than or equal to the Malfare of H star plus epsilon. Regret, on the other hand, measures the price of compromise. How much do individual groups lose by sharing a solution? For example, which pet should we get? One person may want to get a cat, another may want something like a bear, and we can compromise on an intermediate choice like a tiger. We then ask, how disappointed is each individual with the compromise? Nobody asked for a pet tiger, but nobody is too disappointed either, thus the regret is not very high in this situation. Let's consider again the brand name fairness objectives: utilitarian or egalitarian welfare or Malfare, and egalitarian regret. These objectives are easy to understand and they have attractive properties. However, they make extreme trade-offs and admit many valid criticisms. In particular, utilitarian welfare is criticized for not incentivizing redistribution of wealth in an equitable way, whereas egalitarian welfare has the opposite problem. It incentivizes it so heavily that the needs of anyone but the most disadvantaged group are actually ignored. This work treats a broad spectrum of problems that are of real-world interest. There is no one-size-fits-all solution. However, we just explore the problem space to the best of our ability. I argue that statistical learning theory is invaluable to the fair machine learning community. Machine learning often has unforeseen consequences, and a lack of rigor is what got us into this mess. It is not enough to show that a model appears fair on the training data. We need to show that it is also fair on the underlying distribution. This is inherently probabilistic. We want approximately optimality with high probability over randomness in the training data. Underrepresentation of minority groups is a common data quality problem. We cannot learn fairly across groups without understanding each group, and statistical learning theory is the tool to quantify this understanding. In this experiment, we have fair logistic regression on the adult data set. We performed Malfare minimization with the power mean Malfare, and we see that as p increases, the performance on all groups becomes more similar. The disadvantaged groups have improved performance, and the privileged groups have worsening performance as things become more even. However, we don't see quite the same behavior in the training versus the test data. Training performance becomes much more even, but we actually see test performance sometimes become slightly worse or become better by a smaller amount. This is because minority groups are more likely to overfit, in particular as we increase p. Questions like why is overfitting a function of p and how much will each group overfit can be answered with statistical learning theory. Let's visualize this overfitting in this fairness context. We want to learn some hypothesis hat h. The true Malfare is a function of the selected function theta, and the empirical Malfare is also a function of the choice of theta. However, they are not the same function. One is estimated on the data and one is computed on the distribution. Because they're not the same function and they have some fluctuation, the optimizer over the empirical data and the optimizer over the true distribution will not be the same, but the more data we collect, the more similar they will become. we need to make some assumptions if we want to have any sort of guarantee about learning. Learning from data is impossible without assumptions. These are required for rigorous probabilistic guarantees and convenient for computational purposes. Henceforth, we assume we're talking about a Malfare function, and it obeys monotonicity. In other words, increasing the risk values increases the Malfare, and decreasing them decreases the Malfare. This will reduce the problem of bounding our objective to bounding per group expectations and applying monotonicity. We assume also continuity, which gives us that convergence of per group expectations will imply convergence of our objective. And sometimes we assume Lipschitz continuity, which is used to bound the rate of this convergence. Here we see two welfare functions, the p equals 0 or geometric welfare, and the p equals 1 or utilitarian welfare. They're both continuous, they're both monotonic, but the geometric welfare has unbounded derivative as we approach 0, so it is not Lipschitz continuous, making it harder to estimate. If our Malfare function is lambda Lipschitz continuous, then let's assume we have a hypothesis class H, a range R loss function L, and M samples per group. We can then define per group supremum variances as the largest variance within our function family for group J, and Rademacher averages as the Rademacher average of our function family with respect to the distribution J. And then we can use counting and covering arguments to bound these Rademacher averages. And with these quantities, which are all standard in statistical learning theory, we then have uniform convergence bounds not just on expected losses, but on Malfare. We get that the probability that the largest deviation between the true and empirical Malfare values of any function h in our hypothesis class, the probability that that quantity deviates by more than 2 lambda times the largest Rademacher average plus an additional term involving the variance, is bounded. This inequality resembles standard results in uniform convergence theory. We can also replace variances and Rademacher averages with empirical counterparts and thus avoid assuming anything a priori. But wait, there's more. Progressive sampling turns statistical bounds into approximation algorithms. The basic idea is quite simple. We start with a small sample from each group. We then optimize or estimate the objective on the current sample. We terminate if some optimality condition is met, and finally we draw a larger sample and repeat from 2 if we did not terminate. The details are quite onerous. There are many technical issues. We need to correct for statistical error due to multiple comparisons or the early termination problem. We require subtle conditions to ensure termination. However, we can estimate any continuous monotonic fairness objective. Lipschitz continuity is not required. There's another question that arises, which is, as we are sampling dynamically, when do we sample from each group? In order to answer this, we need to ask, how do we measure the sampling cost in multi-group settings? Once we have a model of cost, we apply a greedy optimality heuristic. Which group will yield the largest estimated bound improvement per cost? Unfortunately, that's the end of our time. I invite you all to read the paper today. I promise it's full of rigorous statistical analysis, detailed algorithmic descriptions and correctness proofs, and intuitive examples in practical settings. Thank you very much.